Good morning, Amherst. Tuesday, May 26th, 2020. Last unit of the year, the home stretch, organic chemistry. So get out your packets for organic. You're going to want some writing utensils. You're going to want to take some notes. This is not going to cut it. You're going to need some separate paper. All right, so I'll try to follow along with it as best I can. Organic chemistry. Basically, organic in chemistry means it contains carbon. I know in biology they tell you, oh, alive or once living, and some things they'll say contains carbon and hydrogen. Basically, the chemical definition is if it contains carbon, it is organic. Things like diamond, pure carbon, they are organic in nature. Okay? Now, carbon, element number 6, 1s2, 2s2, 2p6, it's got 4 valence electrons. That means it's going to make 4 bonds. It has to make 4 bonds. And it'll hybridize different ways like we know from our bonding unit, but it's going to make 4 bonds. Now, carbon's got an electronegativity of 2.6. So no matter what atom it's bonding with, the difference in electronegativity is low. So the bonds it makes are covalent bonds. And covalent bonds means they're sharing electrons. These are molecular substances. They're non-electrolytes. They're not ionic. The exception being organic acids. We just finished our unit on acids and bases when the molecule COOH at the end of it, that end H tends to detach, and that molecular substance becomes effectively ionic. Okay, so organic reactions tend to be a lot slower than inorganic reactions, a little less vigorous or violent. If you take organic lab in college, you'll see a lot of times you've got water baths, boiling water baths, and it's might take 10 minutes for this thing to do something. That's not uncommon. It doesn't have to be that way, but they tend to be slower. Organic substances tend to have low melting points and boiling points. They're often nonpolar molecules, NPM, LDF. They're not soluble in water, which is polar. And they're usually combustible. It means they react with oxygen, they burn. Things like gasoline, right? The word isotope is not the same as the word isomer. Isotope refers to things at the atomic level. They're different versions of the same atom. Carbon 12, carbon 13, carbon 14. Different versions of carbon, same number of protons, different number of neutrons. Whereas isomers are at the molecular level. They're the same group of atoms. You just put them together in a different arrangement. So isotopes, carbon 12, 13, 14, same number of protons, different number of neutrons. So it's a different mass number, same atomic number. Isomer, you get the same group of atoms, you just arrange them differently. You have the same molecular formula, the inventory, but a different structural formula. They're arranged differerently, so their structures are different. The word allotropes shows up from time to time. They're different forms of the same element, like diamond, graphite, and Buckminster fullerenes or buckyballs. Those are forms of pure carbon. Oxygen and ozone, those are forms of pure oxygen. Those are allotropes. Not as big a deal. The word hydrocarbon means the substance contains hydrogen and carbon, nothing else. If it's got even one atom that isn't hydrogen or carbon, it is not a hydrocarbon. Now, crude oil, the basis of the world economy still, is a mixture of hydrocarbons in the ground. So hydrogen's got electronegativity of 2.2 and carbon is 2.6. Your difference is 0.4. Many organic textbooks will describe the bond between carbon and hydrogen as essentially nonpolar covalent. I know we said 0.0 meant it was nonpolar equal sharing, and 0.4 seems like it's a fair difference away, but depends on who you talk to. Organic textbooks will say that this is basically a nonpolar covalent bond. In any event, hydrocarbons tend to be symmetric nonpolar molecules, NPM, LDF. The bigger they are, the stronger they are. So the larger the hydrocarbon, the better they stick together, the higher the boiling point, the higher the melting point. So if you take crude oil and you heat it up and you separate these substances based on their boiling point in a process called fractional distillation, take your crude oil, heat it up. As it goes up, it starts to cool down and recondense. So the smallest hydrocarbon, CH4 methane, is often burned out of the top. But your low GFM hydrocarbons will be the hardest to condense, and you might actually have to increase pressure or whatnot. But things like propane and butane, which are gases at room temperature, they're going to come out of the top of the column. As you get larger and larger, by the time you hit things like pentane and hexane, a little bigger octane, which is gasoline, or diesel fuel, which is dodecane, that's 12 carbons, they're in the middle. And the bigger the hydrocarbon gets, the higher the boiling point. You get things like motor oil or tar and asphalt down at the bottom. You've probably driven by some of the refineries. South Buffalo's got continuous flame on one of the, I think it's Allied Chemical going on there. And basically any oil refinery, this is what they're doing. They're separating the components of the crude oil, the hydrocarbons, based on their boiling point. That process is called fractional distillation. So hydrocarbons come in three what we call homologous series. Something about them is the same. Well, it's the same algebraic relationship between the number of carbons and the number of hydrogens. So here's table Q, and you'll see that there are alkanes, alkenes, and alkynes, where N is the number of carbons in the formula. Ein, and ein, the suffix. Alkanes are described as saturated hydrocarbons, alkenes and alkynes are unsaturated, and that's the same context as when you hear things like unsaturated versus saturated fat. It's a matter of, are there as many hydrogens on that carbon chain as possible, or is it potentially capable, am I capable of putting more hydrogens on there? So saturated hydrocarbons, alkanes, contain the maximum number of hydrogens on there. Alkenes have one double bond in between two of the carbons. So you can break open that double bond and stick two carbons on there. You can make them a little bit heavier. Alkynes have a triple bond. So all single bonds for alkanes, one, not all, just one double bond for alkenes, and one triple bond for alkynes. Carbon to carbon single, carbon to carbon double, carbon to carbon triple. That's how you recognize alkenes, alkanes, alkenes, and alkynes. So the general formula, if you max out the number of hydrogens, if you have N carbons, you have twice as many and two more hydrogens. If I take off two hydrogens and condense the carbons back onto each other and form a double bond, just take two of them out, so it's CnH2n. If I do it again to form that triple bond, take two more out, so it's CnH2n minus 2. So the examples I give you here in table Q, you've got two carbons for each of them. So this one, with all single bonds, C2H6, often they don't write the H's. If you see the dash, that's acceptable. You don't have to write in the H, but if you don't write the dash, it's wrong. So C2H6, yeah, okay, 2 times 3 plus 2. 1, 2, 3, 2 times 2 plus 2. 1, 2, 3, 4, 5, 6. Okay, yeah, 2 times 2 plus 2 is 6. It works. Twice as many CnH2n. 1, 2, 3, 4. Yeah, it works. Twice as many minus 2. So 2 times 2 is 4 minus 2 is 2. Yeah, 2 hydrogens. Yes, that would work. So in naming a hydrocarbon, the prefix gives you the number of carbons, and the suffix gives you the number of hydrogens based on the bonding. So if you take a look at table P, you've got 1 through 10 here. Now, you're going to end up memorizing that just because it's language. You end up, if you need to refer back to it, you can, but it's not that much. Here's a mnemonic device to help you remember. Many elephants prefer buttered peanuts. Meth, eth, prop, bute, pent. In my first year of teaching at South Park High School, I said, okay, 6 through 10, I wasn't familiar with a mnemonic device for those, and one of the girls in my class immediately came up with happy hippos often need daisies. Kind of fit with the elephants. Thought it was nice. Mind you, it took all of 10 to 15 seconds for my students to come up with an alternative to happy hippos often need daisies, and the only two words they kept in there were often need, and I'll leave the rest of that up to you. First member of the alkane series, okay, the simplest hydrocarbon is methane. It's the only one carbon member of any of the series, because you can't have a double or a triple bond unless you have two carbons. So the first member of the alkane series is methane. 1 carbon, 2 times 1 plus 2, 4 hydrogens. Yeah, methane. They call it an alkane. You can't have a methene or a methine because you need a double bond in between two carbons. So the first members of these series are ethene and ethine. Now, old habits die hard. Ethene used to be called ethylene. You'll still hear that, ethylene sometimes. Enes were illenes, but they were even applied, not consistently. Ethine used to be called acetylene. It's still called acetylene for welding torches, acetylene torches. So, old habits die hard. You're going to have to become familiar with some of the old names. We'll try and give you a heads up as we go through all of that. But eth, in any event, means 2 carbons. And if you got ethane, they're all single bonds. This is what is going through on your table here. All single bonds, here's 1 carbon, here's 2 carbons. Fill them up, you've got 6 hydrogens. In ethene, you've got the double bond here. That leaves you with only 4 more hydrogens. And ethine, you've got the triple bond here. It leaves you with only 2. Now, these are drawn very nicely, following Vesper, spreading out like that, but quite frankly, as long as you show carbon having 4 bonds, I don't care if you make them looking like in the X shape here, or this is drawn out, or if it was kind of like a U, I don't really care. As long as you've got 4 carbons on every, 4 bonds on every carbon. All right, so that just goes through the whole table there. Now, if you have all one chain, don't have to be all single bonds, but just one chain of carbon to carbon, no branches, that's called a normal isomer, just unbranched. So if I have 4 in a row, 1, 2, 3, 4, well, that's going to be bute. Don't call it but, it's bute. Okay? It's got single bonds. Well, that's going to be butane. It has no branches, so that's normal butane or N-butane. 4 carbons, bute, single bonds, ane, 1 long chain, normal. Structural formula is the drawing. The molecular formula is simply inventory, C4H10. 1, 2, 3, 4, 3, 5, 7, 8, 9, 10. The IUPAC name is N-butane, and if they just say butane, it implies you've got the normal isomer. We will come across something in our packets called the condensed structural formula, which says, well, what if I just consider these in a row? Like, what is that? Well, that's carbon with 3 hydrogens, so that's CH3, followed by CH2, followed by CH2, and ending with CH3. I suppose you could condense that even further and say it's CH3, then it's got CH2 taken twice, and then you've got CH3 again. But you can't condense these two together because they're not touching each other. This gives you an idea of how to build the condensed structural formula, how to build the structural formula. If you just said CH3 twice and CH2 twice, you could end up with alternatives that would not be acceptable. So, if I rearrange these atoms, put them together differently, 1, 2, 3 there, and 1 either down below or up top, not on the end. It doesn't matter, like, if I went like this and curved, that's still okay, that's still one chain. But here, this is in the middle of a chain. And single bonds can rotate and spin, so that could end up either above or below, it really doesn't matter. Well, this is a different structural formula than this. They're going to have different chemical and physical properties. They're going to have different boiling points. They're going to have different densities. They're going to have different reactivities. They are not the same compound. You can't call them the same thing. They're going to have the same molecular formula of C4H10, but since they have different structural formulas, they get different names. So how do you do that? You find the longest continuous carbon-to-carbon chain, and that's going to be the root of your name for the compound. Then you say, well, what's attached to that chain? Where is it attached? And you always pick the lowest possible numbers. I'll do a few examples of that, show you how it works. You got to count from one direction also. You can't, if you've got more than one thing attached, you can't count one way for this attachment and one way from that attachment. Once you pick a direction, that's your direction. You always pick the direction that gives you the lowest possible numbers. So here we go. In this chain, I've got 1, 2, 3 carbons there. I could have said 1, 2, 3 or 1, 2, 3. It doesn't really matter. Either way, they're 3. And if I number them, 1, 2, 3 or 1, 2, 3, either way, this extra carbon is on the middle, number 2 carbon. So my longest chain is 3. My prefix is prop. I've got 1 carbon here. The prefix for 1 carbon is meth. It's on the 2nd carbon of the chain, no matter which way I count. All of the bonds in the chain are singles, so the suffix is going to be ane, so this is propane with a meth, or methyl, YL, make it an adjective, group, on the 2nd carbon of that chain. So, no matter which way I count, 1, 2, 3, yeah, that's a methyl group on the 2nd carbon. 1, 2, 3, yeah, that's a methyl group on the 2nd carbon. Either way, it's prop, single bonds, ane, with a methyl group on number 2. It's 2, it's supposed to be dash, they put 2 dash methyl propane. Now, this 2 is redundant, it's not wrong, it's just in a group of 3, 1, 2, 3, there is only one middle position. You can't have a 1 or the last position. Like if I put this onto here, you call it 1 methyl propane? No, you're back to normal butane, 4 in a row. So you can't do that. So you can't have 1 methyl. There's only one middle position on 3. So it's methyl propane or 2 methyl propane. And I recommend, at least for the next couple days, use the numbers no matter what if they're redundant. 2-methylpropane and methylpropane are identical. Let's take a look at this one. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. 5 wins over 3. My longest chain is 5 in a row. Okay. So here's 5 in a row. 5 is pent. All single bonds. Single bonds, those are anes. That's a 1-carbon group. That's meth, but we'll make it an adjective. That's methyl, oh, that's the same color. Methyl propane. All right, so, or I'm sorry, methyl pentane. So now your question is, here's meth, ill, pent, ane. What number of the chain is it on? Is it on number 1, 2, 3, 4 out of 5? Or is it number 1, 2, 3, 4 out of 5? 1, 2, 3, 4, 5 is my longest chain. Or counting back the other way. 1, 2, 3, 4, 5. 2 is lower than 4. This is 2-methylpentane. You always pick the lowest possible number. So one thing about IUPAC naming conventions, it's very, very consistent. So if I was going to do a condensed structural formula here, and that's number 2, I would say, well, okay, let me get a good color here. I'll just go back to black. This would be the first member of my chain. I would call this CH3. Then I've got this group here, CH3. Then I've got CH2, CH2, CH3. I could probably condense those a little bit, but I'll just leave it like that. I'm least concerned about the condensed structural formula, but you will find it useful to become fluent in that because you've got a slightly modified version of it here on table R. All right. What about something with double or triple bonds? Let's do enes. We've got ene here and ene here. 1 butene versus 2 butene. All right, so the ene tells me I'm going to have a double bond. Bute tells me I'm going to have 4 carbons. The number in this case tells me where the double bond starts. So 1, 2, 3, 4 versus 1, 2, 3, 4. All right, one of the bonds has to be double. This one, the double bond starts in the first carbon, so I'll just put a double bond there. All of the others are singles. Carbon has to make 4 bonds. 1, 2, 3, 4. Yes, the carbon made 4. 1, 2, 3, 4. It doesn't matter if you draw it up or down. We'll talk about that in a minute. 1, 2, 3, 4. 1, 2, 3, 4. So this is C4, H, 1, 2, 3, 4, 5, 6, 7, 8. C4, H8. Hand's not doing what the mouth is doing. That's okay. But that would make sense for the ene, twice as many. 2 times 4 is 8. Okay, so it's got the molecular formula C4H8. What about the second one? 2-butene. Starting on the second carbon, make your double bond. All of the others are singles. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. C4H8. Again, yes, these are indeed isomers. They have the same molecular formula, but different structural formulas. So I could do condensed structural formula here. I could say this would be CH2, CH, CH2, CH3, and this one would be CH3, CH, CH, CH3. Just kind of going in order. Different arrangements give you different properties. These are not the same compound. Now, something that got dropped out of the Regents curriculum years ago, but there's a little side note here, it's not testable, but when you have a double bond, all of a sudden you lose the ability to rotate. So let's look for a second at 2-butene. Let me get myself another sheet of paper here. Here's something for you future organic chemists. If I look at 2-butene, there are two ways I could have drawn that. With my hydrogens both facing up or down, the molecule can rotate, or I could have had one of the hydrogens facing up and one facing down. The single bonds always have the ability to rotate. The double bond locks them into place, so this arrangement is an isomer of this arrangement. When both of the hydrogens are on the same side of the bond, they call this the Cysts Isomer. Kind of forms a C, so cis. When the attachments, the hydrogens that are attached, go across the bond, they're on opposite sides, they call this the trans isomer. Cis 2-butene or trans 2-butene. This is what they're talking about when you hear about trans fats being no good for you. It turns out that, cis isomers tend to be easier for our body to metabolize, but trans fats tend to get a little bit more difficult to break down. Our body tends to store this. This is what clogs your arteries and whatnot. So it's relevant in today's society, although it hasn't been part of the curriculum since, 2000. Still, you're taking honors chem, so now you know. Cis isomers, trans isomers, this is not part of the curriculum, but it can't hurt to know it. All right, let's continue on. What if we wanted to do all possible isomers of C6H14? What is that? C6H14. Well, let's see. 2 times 6 plus 2 is 14. 6 is hex. 2 and plus 2 is ane. So all possible isomers of hexane. All right. Let's start with the normal isomer. This is where I wish we had model kits, but that's fine. Here's the first one. N. Hexane. 1, 2, 3, 4, 5, 6. Single bonds. Carbon has to make 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 3, 4, and 3 more there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, that's going to work. That's normal hexane. It is indeed C6H14. How can I rearrange that? Well, if I had model kits, I would say snap one of the carbons off the end. Take a hydrogen off somewhere in the middle and just flip-flop them. So, what if I did this? I go 1, 2, 3, 4, 5, all singles. Carbon has to make 4 bonds. So I've kind of detached that. I can't put it back on the end. It doesn't matter if I go top, bottom, left, or right. Any of the ends, it's just still making 6 in a row. But I could put it here, or I could put it here, or I could put it here, the interior things, but this would be number 2, and this would be number 2, so these two would be the same. Right? If I go 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, if I put it here or I put it here, they're both number 2. But on either case, my longest chain here is 5 in a row, so that's pent. It's still C6H14. It's still got single bonds, so it's pentane. Where do you want to put that extra carbon? Well, let's put it here. That's on the number 2 of the chain. So 2, there's a 1 carbon group there, 2-methyl pentane. And what if I had put it one more inside? 1, 2, 3, 4, 5 singles. Fill them up. If I put it here, it's on number 3. It's still C6H14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. But now it's on the number 3 of the chain, so this is 3 methyl pentane. But we're not done. So, well, if you can go on number 2, 2 and 4 would be the same, so you might think 1, 2, 3, 4, 5 singles, fill them up. You might think here, but that's still on number 2. So we've already used that one. That doesn't mean we're done. What if I pop another one off the end there? Now I've got 1, 2, 3, 4. Fill them up. I've got 2 carbons to attach, CH3 methyl groups to attach. I'll tell you what, I can't go on the ends because that just makes my chain longer. Let's put one here and one here. Sometimes they write this like this, 1, 2, 3, 4. Because the sticks get confusing, they go, it's a CH3 group up here and it's a CH3 group here. It just means the same thing. That is CH3. That's CH3. What's your longest chain? 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. 4 is my longest chain. 1, 2, 3, 4. 4 is my longest chain, no matter what. Okay, 4 is my longest chain. My prefix is bute. Single bonds, my suffix is ane. Altogether, I've got 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 8, 11, 12, 13, 14. It's still an isomer, C6H14. I've got a methyl group there, and I've got a methyl group there. So I've got 2 methyls. All right, where are they? Are they on number 1, 2, 3, 4, or number 1, 2, 3, 4? They're on number 2. So what do you call this? Well, each attachment gets a number. So I could call this 2-methyl dash 2-methyl butane, or I could abbreviate that a bit and go, well, it's 2, 2 dash dimethyl butane. Either of those is acceptable. Okay. But what if I have another one? What if I go one here and one here? So, this is isomer number 5. 1, 2, 3, 4. Fill them up. Let's put a methyl on number 2 and a methyl on number 3, and I'll just put one up and one down just to separate them, but they could have been, it's a single bond, there is no cis or trans thing. Longest chain 4, it's still bute. Single bonds, it's still ane. It's got a methyl here and a methyl here. 1, 2, 3, 4, or 1, 2, 3, 4. Either way, on the second and on the third. But I can't call this one number 2 and that one number 2. You have to count from one direction. So you can't count this way and that way. So if this is number 2, this is number 3. If this is number 2, this is number 3. So I could call this 2-methyl, 3-methyl butane, or 2, 3 dimethyl butane. That's what I prefer. I like that. But if you have 2 attachments, you need 2 numbers, okay? So now, part of your homework, if you look at your worksheet packet, they're going to ask you to recreate that so you can follow along with this video. But now, ask yourself, what if I tried to go shorter? Or what if I tried to take those 2 and combine them elsewhere? Here's some of the pitfalls people run into. They go, what if I had 1, 2, 3, 4, and I had taken 2 of my carbons off? What if I stick those carbons together? So somewhere I'm going to put that. Okay? Well, you only have 2 interior positions, and they're the same. This is number 2, or this is number 2. So people think, well, what if I take this ethyl group? It's got 2 carbons in a row there. We'll call it an ethyl group. What if I try to do that and put it here? We'll go here. people think, can't I call this an ethyl group on the number 2 carbon of a 4-membered chain? You need to be careful here. Think about this. You go, okay, 1, 2, 3, 4. They think, okay, it's butane, single bonds. And on number 2, they got an ethyl group. They're thinking 2-ethyl-butane. But that's a little deceiving, because check this out. 1, 2, 3, 4, 5. This is my chain. There are 5 in a row right there. You always look for the longest chain. So if that's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, either way, this is 3-methyl-propane, which was one of our earlier isomers. So you need to be careful when you arrange these. Even though you came up with what you think is a different drawing, still count your carbons in a row. Remember, your longest chain is the root of your word. All right, last thing for today, because this is already a long video. We're going to talk about halides or halocarbons, as table R would call them, and the worksheet calls them alkyl halides. This means on a carbon chain you stick a halogen. Well, the first thing you need to know about that is you no longer have a hydrocarbon, and that is because it contains an atom other than hydrogen and carbon. So if you put fluorine, chlorine, bromine, or iodine onto a carbon-based chain, you have an alkyl halide, just a halide, or a halocarbon. It's not a hydrocarbon. But the naming convention doesn't really change that much. You'll notice instead of YL to make it an adjective, they go O. So it's not fluoryl, it's fluoro, chloro, bromo, or iodo. I particularly like iodo, particularly when you have 2 of them. Diiodo. Wow. Diiodo. Sounds nice. All right, so they're not hydrocarbons, but the naming is similar. For example, chloromethane. If you say, all right, meth, 1 carbon, ane, well, yeah, single bond. So if I had 1, 2, 3, 4 carbon, or 4 hydrogens on that carbon, I'd have methane. Take one of the hydrogens off, put a chlorine on there. CH3Cl. That's how they do the molecular formula. Carbons, then hydrogens, and whatever else. It's just an inventory. Chloromethane, it doesn't matter which one you put it on. That molecule can roll and tumble in space. Here's my structural formula. Here's my molecular formula. Here's my IUPAC name. And I suppose there is no way to condense that. You could say it's CH3Cl, CH3 here, and then Cl. So there's no condensed structural formula. Okay? If I had 2 carbons here, 1, 2, doesn't matter if I put the chlorine here, or here, or here, or here, any of them are all the same. C2H5Cl, this would be F, 2 chlorines, right? And chloroethane, it's on the first carbon here, or it's on the first carbon here. I don't need a number. I could condense it and say CH3, CH2Cl. That would match my molecular formula and my structural formula. All right, what if I had 3 of them? What if I had propane, and I'm going to put a chlorine on there? I could put it on the end, or I could put it in the middle. This end or that end, it doesn't matter. They're either number 1 or in the middle, either top or bottom, doesn't really matter. And when you're on the end, it doesn't have to be sticking out. Anywhere on this carbon or anywhere on this carbon, they're all equivalent. And here it is in the middle up here. So C3, 1, 2, 3, H, 1, 2, 3, 4, 5, 6, 7, yeah, Cl, C3H7Cl. C3, yeah, 1, 2, 3, 4, 5, 6, 7, H7Cl. So they're the same molecular formula. These are isomers. This one, I'm going to count from this end. So I'll put the Cl last. CH3, CH2, CH2Cl. CH3, CH2, CH2Cl. Okay? This one, CH3, CHCl, CH3. CH3, there it is. CHCl, there's really a hydrogen there, right? So CHCl and then CH3. Okay, so they have different condensed structural formulas. They have the same molecular formula. These are indeed isomers. So for the last thing for today, which I think this might be our longest video, what if we did all of the isomers of dichloropropane? So dichloropropane right off the bat, we're going to have 2 chlorines on there. Prop tells me I've got 3 carbons. Ane tells me I've got single bonds between them. All right, so dichloropropane. Well, 1, 2, 3. Here's, if these are all hydrogens, that's propane, C3H8, but I'm going to take 2 of those off and put chlorines on there. So what if I put them both here? Both on the first one. I call this 1,1 dichloro-propane. Okay, that's one of the isomers. What if I put them here and here? Both in the middle. 2, 2 dichloro-propane. Could I have 3, 3? No, that would be 1, 1 again. All right. So, what if I split them up? Put one here and one here. 1, 3 dichloro-propane. If that's number 1, that's number 2, that's number 3. If that's number 1, that's number 2, that's number 3. I can't call them both 1, so it's 1, 3 dichloropropane. And finally, what if I did this? One on the first one, one on the second one. 1, 2 dichloropropane. Could I go 2, 3? No, because that would still be 1, 2. This and that are the same thing. That's literally, take a look at the marker. The cap's on the left, right? Well, just roll it over, now the cap's on the right, but I didn't change the actual compound. Take the chlorines and just flip them to the other side. So this is still 1, 2. So I think we've done all of our isomers of dichloropropane. So we had 1, 1 dichloropropane, we had 2, 2 dichloropropane, we had 1, 3 dichloropropane, and we had 1, 2 dichloropropane, and all of them had 3 carbons and 6 hydrogens and 2 chlorines. They would all have the same molecular formula. They would have different structural formulas. They would have different condensed structural formulas as well. Your homework. I know it's a pretty big jump today, but that's all right. This is the final unit. You're going to turn to worksheet 2. We've just done a bunch of it. And you are going to come up with the IUPAC name or the structural formula and some other basic stuff here for these hydrocarbons and these halides. So it goes up to number 23, but we've done a bunch of those. That's your homework for today. We'll pick it up here tomorrow. Have a good one.